This one right here, so a left sum and 4 subintervals. So the left sum, we're just going to be using the left edge of each interval to determine the height. So the first interval would be from 0 to 1, right? So for part A, we would say the base length is 1, and the height is either 18 or 32. Which one would you pick for a left sum? 18. Okay, so 1 times 18 plus, the next interval is from 1 to 2. There we go. So once again, the base length is 1, or should the base length be 2 because it ends at 2? Because isn't it the difference between the two of them? Yeah, okay, so 1, and then we'll use the left edge, which is 32. The next interval is from 2 to 5. And so this one, the base length is not 1. This time it is 3. That's right. So 3, and then the left edge is, or the left height, I should say, is 72. Plus the final interval goes from 5 to 8. That is also a distance of 3, and we'd use 200. And I'm assuming that you guys can multiply and add well enough to handle that. Is that good as far as the setup goes? Did you take it all the way through? So let's see here. 50, 266, 866? Okay, so 866, we're good? Okay, so B, same sort of thing. In fact, it's the exact same thing, except instead of using all the left heights, we'll use the right heights. So all of our bases should be the same. So 1, but instead of times 18, it'll be times 32. And instead of 32, it'll be times 72. And it'll be 3 again, but instead of times 72, it'll be 200. And 3 again, but now it's times 242. This will be a little more interesting. So did you guys get 104, 704, oh boy, 726, 1430? 1430? I'm a math nerd. I have a math nerd card back there. Okay, so it's really important we be able to distinguish between a left sum and a right sum. Okay, as silly as that sounds, I want to be able to make sure we do that right and not mix them up. You guys all okay with that? Yeah. Okay, now the midpoint sum is the one we talked about a little bit there at the end. So we're only supposed to use 2 subintervals, so I'm going to get rid of all this stuff as best I can. So the 2 subintervals really, if we're going to do a midpoint sum, have to be from 0 to 2 and then from 2 to 8. That make sense? So for the first base, we go from 0 to 2, so it's going to be a length of 2. But then do we use the 18, the 32, or the 72? 32. We use the height right there in the middle, so 2 times 32. And then the other one goes from 2 to 8, so the base length is 6. And once again, we could choose the 72, the 200, or the 242, but we're doing a midpoint sum, so we've got to use the 200. So this one, as you can see, instead of having 4 subintervals and 4 rectangles, it's only got 2, so it's 64 plus 1200, so how about 1264? Is that good? Okay, so just a point, bless you, just a point here that I think is really important. Let's say it's a quiz or a test, and there's some question like this where it says use a left sum, right sum, midpoint sum, whatever. You guys are all good at arithmetic, and you can figure these answers out. In fact, if the numbers are smaller, I'm sure you could just like whip it out really quick without really showing much work at all. But it's very important that you have evidence on your paper that you did a left sum. Bless you. So to see the evidence of a left sum, I need to basically see base times height plus base times height plus base times height, dot, dot, dot. And then if you want to go from there straight to an answer, you can. But I will say, as you guys know, maybe Sean doesn't know this, for sure on the AP test, on a free response scenario, you don't have to simplify. You don't. So let's say that question A was an actual question on one of my tests or the AP test. I want to get you into the habit of realizing what you can and can't do and maybe what you should or shouldn't do. Most often I would say in these scenarios, let's say we're doing question A, it'll say, use a left sum to approximate such and such. It'll be worth 2 points. The first point is basically they showed evidence that they used the left sum. That's point number 1. And point number 2 is the answer. The truth is, for A, if you just wrote what I have up there, you get both points. Because you showed evidence of a left sum, and isn't your answer numerically equivalent to whatever the answer was? So when it comes, you can do it however you want in here, but I'll just encourage you really strongly when we get closer to the AP test, just stop. Stop. Resist the urge to simplify. And stop right there. Only applies to arithmetic. You can't say, later on, we'll talk about definite integrals. You can't say, hey, I think the answer is the integral from 2 to 4 of f of x And I'm just going to leave it like that because I don't have to simplify. Well, that you do, right? Because that's calculus. You need to actually complete those processes. But if the only thing remaining is just some basic arithmetic that a 7th grader could do or something like that, then just leave it alone. Because even though you're all like really smart math people, you might still mess up 7th grade math. We've all done it, right? And so just leave it alone and call it good. All right, we all happy with that? Okay, awesome. Well, let's move on then. So let's see here. Yeah, there we go. All right, so do you remember Riemann sums from last year? Because they remember you. I heard they liked you. Cameron's like, no, they don't. All right, so Riemann sums. The good news is about these Riemann sums is I feel like the nastiest part of these Riemann sums would be the completion of the process and all the algebra and little details that could potentially get lost that you need to have right in order to complete the process really well. And the good news is I really don't think, it didn't happen last year. And I don't think it's ever going to happen because that would just be really a huge amount of time spent on just like one little thing. I think what they're going to have you do, just like we kind of did last year, is basically be able to match a Riemann sum with an integral and make it all kind of make sense matching-wise, but they're not going to have you complete this massive process that honestly would take the better part of a page with lots and lots of details. So that's kind of the good news. So this has, some reminders about sigma notation, and if we decide to like complete a whole process, we'll maybe use some of these formulas to kind of help us complete that process. But for the moment, we're not going to worry too much about that. The definition of area using a Riemann sum or a limiting process is actually relatively simple. Let's break this down, and let's just talk about what this is. So if f is continuous and non-negative, then the area of the region bounded by the graph of f, the x-axis and those two vertical lines there, is given by this right here. And I just want to kind of break this down. So there's the area formula. I want to break this down into its really simple parts. We can kind of realize what is actually going on. So we have limit as n goes to infinity. N will stand for the number of little sub-intervals. And so we want the number of sub-intervals to approach infinity. So that's just there for the moment. And then you all have seen this sigma before. What does sigma essentially mean? Add a bunch of stuff up, right? Whatever we need to add up, we'll want to add that stuff up. But then this is what I want to focus on right here. Delta x, like if you refer over here to the page, delta x, it says delta x is that difference right there. So that's delta x. In relation to that little shape in the region there, what is delta x? It's a rectangle, so let's be a little more specific. Base. Length, base, same thing, right? So it's a base length, let's call it. So that is the base. And then f of ci is right there, and we can see that that's right there. In relation to the shape, what's that? Height. That's correct. And so to be able to construct these Riemann sums, it really comes down to this. So let me just let the cat out of the bag. They're all going to have limit as n goes to infinity. They're all going to have sigma from I equals 1 to n. So like every single one of them will have that. It's going to come down to, can we correctly define the height in general as well as the base length? The way I practiced this last year with my students was we're going to start off with the easiest part and work our way up to the most difficult part. That makes sense? So let's try a couple of these here. I know there might be some trepidation, a little bit of fear, possibly. I think I'm really confident we can work through this, especially since you've seen it before. I'm pretty sure we can do this. So let's take a look here. Number 3, it says write a Riemann sum to express the area under the curve for that function right there on the interval 0 to 1. What'd she do? Okay. Oh, okay. I just wanted to laugh too. Oops. All right, so we look at this graph right here. It's a cubic, and of course cubics do something like that. It's supposed to be symmetrical. I tried. And we're looking at the interval from 0 to 1, so show our vertical down there, and of course we're talking about that nice, beautiful purple region right there. Make sense? Okay. So we're supposed to use a Riemann sum to do this. And so, like I told you, the easiest part of this is the stuff that's always there. So Riemann sum will be the limit as n goes to infinity of sigma from I equals 1 rectangle all the way to n rectangles. Every single Riemann sum, that's supposed to be an I. Sometimes the I is a J, just so you know, depending if you maybe you look at some other resource. I think the AP stuff, and I'll try to keep mine consistent. It's always going to be I. So they'll always have that. So there should be no issue with writing that part down. Now let's see if we can get the base and the height figured out. I always feel like the base is the easiest part. So the way that you figure out the base is you look at the interval. So the interval goes from 0 to 1, and we want to decide in total how wide is the full interval. 1, right? 1 minus 0, that's how you get the width. Of course, 0 to 1, you can see that it's 1. But then we want to divide that region up into how many little subintervals? We want to be flexible. We don't want to use 4 or 10 or 20. We want it to be n, right? So just to parallel kind of just the more numerical approach, like if I said, hey, the full interval is 0 to 1, and I want to divide it up into 10 subintervals, how wide would each subinterval be? 1 divided by 10, or 0.1, right? So if I wanted to divide it up into 20 subintervals, it would be 1, the full width, divided by 20. So whatever the full width is, you want to divide it by the number of rectangles, and we want to be flexible. We don't want to be stuck with 10 or 20 or 1,000. We want it to be n, because we want to be able to make n whatever we want. Does that make sense? So the base length will be the full width divided by the number of rectangles. In this case, it's n. So I feel like getting the limit and the sigma, that's the easiest part. Getting the base length is like the second easiest part. But now getting the height, that's the hardest part. So let's finish with that. So let's just draw in a height here, or maybe a rectangle. So I'll just do a right sum rectangle, something like that. Wouldn't it be fair to say that the height of that rectangle is determined by the height of the curve?
Yes.
Isn't the curve telling the rectangle how tall to be? Do you see how that upper right endpoint is on the curve? So whatever the y coordinate is at that x value, so this point right here is, x comma y. Whoops. So whatever that y coordinate is, that is exactly as high as the rectangle's height. So we look back and we're like, well, all right, well, how tall is the curve? Like, what expresses the height of the curve? What tells the curve how tall to be? X cubed, right? So you look at this function, well, it's f of x equals x cubed. And of course, we know that y functions similarly to f of x, right? So it's saying that the height of the curve depends on the input cubed. So what I'm going to say then, fine, my rectangle then is going to have a height of input cubed. I haven't filled in the details yet, but I know it's going to be input cubed is going to be my height. Still following okay? And this is tough though, right? To get the right input, because is the input going to be the same all the way across? Well, the fact that we're moving all the way across tells you that it's not going to be the same input. So here's how we develop the input. We want to start off with the lowest conceivable input on our interval, which is, in this case, 0, right? The far left edge is 0. So that's where we would start with our inputs. But we know that we're going to move our way across the region. And so we're going to add a little bit each time. So 0, of course, is right there on the origin. And then I've got, another rectangle. Maybe it'd be over there. I'm obviously drawing some very large rectangles just because I don't want to draw a bunch of tiny ones. So if you think about it, for me to get over to the next height, how much am I going to have to add to that 0 to get the correct input? Say again? Right. Aren't I going to have to add the width of a rectangle to get to the next rectangle? And each rectangle is 1 over ny. So here's where I can almost get it, but not quite. If I just put plus 1 over n, that's the right sense, but it's not the right detail, right? Because wouldn't that just stop me at the first rectangle?
I over n.
And I have to include the I, right? So the I is my summation element, so I'm just going to put 1 over n times I, or as you said, Lenny, I over n is the same thing. And so with that summation element, if you look back to the sigma, the summation element, I, is going to go from 1 to 2 to 3 to 4 to 5, ... all the way up to n. So we're essentially saying, well, we want n to head towards infinity. And so because that I is in there, That's going to be heading towards from 1 up to infinity as well. Therefore, taking the number of rectangles from some finite number to approaching infinity, therefore making the width approach 0 and filling up the shape or the region perfectly. That makes sense? Remembering this okay from last year? We spent a lot of time on it. Sean, I don't know where you stand, but you seem like you're doing okay. Kind of, do you have any questions? We're going to practice. It's almost like you don't know what you don't know. You know that it could get more complicated. Okay, yeah, it's very possible. This is actually, could very well be a pre-calculus scenario, right? Because we're not doing any derivatives, right? But the concept of area, you know, it's maybe it would be a little bit tough. But so this is where we would stop here, because all this says we have to do is write a Riemann sum to express the area under the curve. We don't really have to take this any further. We could. We definitely could by, you know, cubing the 1 over ni, doing some multiplying, getting some stuff out of the sigma, using those formulas we saw earlier, and we could eventually boil it down to what we know to be the answer. Because I guess I don't know about Sean yet, but we all, if faced with this, if we weren't told to use a Riemann sum to find the area, what would you use? A definite integral, right? You'd go integral from where to where? 0 to 1 of x cubed, do some antiderivatives and FTC1, and voila, probably 45 seconds later, you're done. This process probably wouldn't take 45 seconds. It would take a little longer than that. So my point being, if you're asked to just set it up, we just set it up. But there is just algebra and arithmetic left to get this finished, something you could do. And I would encourage you, if you have a little bit of time, you're thinking about the chapter 4 stuff later, and you want to just explore this a little bit, once you know the FTC1, you can come up with the answer pretty quick. I would encourage you to take something like this and see if you can arrive at what you know the answer to be. That makes sense? Like, you can do integrals and get the answer. Maybe take a Riemann sum, see if you can make it get there knowing what the answer should be. It's an interesting exercise for sure. Okay, so let's do another one, number 4. It's right there. So check this one out. This one says, so this one actually encourages us to kind of go all the way with our answer. I don't know that we'll do that. This says, find the area using the limit process of the region bounded by the graph of 4 minus x squared, the x-axis, and the lines x equals 1 and x equals 2, as shown below. So let's see, at the very least, let's see if we can set this up, and then we'll check. If we set it up, I'm assuming y'all had the limit as n goes to infinity, sigma from I equals 1 to n. Now let's set up our base. What did you guys have for a base length of each rectangle?
1 over n.
You have to be 1 over n. So we're going from 1 to 2 now. So the full interval width is 2 minus 1, right? And so we divide that up into n rectangles, so 1 over n. And then as far as the input, or as far as the output goes, the output is based on f of x. And so it's going to be 4 minus something squared. And it's just up to us really to fill out what the input is. So what did you guys have for the lowest possible input on this interval? 1. Good. So it's going to be 1 plus what?
1 over n.
1 over n I is correct. So we're basically going to move to the right 1 over n each time to get to the next rectangle. So I'm debating about this. I don't know if I really want to do this or not. I don't think I was debating about going all the way with this. We'd have to do some foiling. It's not that bad. I don't know. Let's
Do it.
You want to do it? You want to do it? Okay, fair enough. So I'm not going to do it if you're just going to sit there and watch. Let's do this together. Let's do this together. Okay, so first thing I'm going to do is FOIL. So let's FOIL out the 1 plus 1 over ni squared. Let's multiply it out. So we're going to have the limit this whole time, and we're going to have the sigma this whole time, and the 1 over n is there, and the 4 minus. So when you FOIL this, it's going to be what? 1 plus 1 over ni plus 1 over ni. So I'm going to put that down as 2 over ni plus, what would be your last product?
1 over ni squared.
1 over n squared, I squared?
I over n squared.
I squared.
Over n squared.
I squared over n squared? Okay, yeah, I just wanted to make sure we had our squareds in the right places. All right, so there's that right there. And then, let's see here, let's go ahead and do 4 minus and distribute some minus signs and add some like terms. So we're going to have the limit and the sigma and the 1 over n still. So it's going to be 3 minus 2 over n minus I squared over n squared. Still hanging in there? Oh, I lost an I. 2 over n I. 2I over n. All right. Still good? Last thing I think I will do is distribute the 1 over n throughout, and then we're going to have to turn to some formulas from before, some of which I have memorized, other which I probably have forgotten. So it's going to be 3 over n minus 2 over n squared I minus I squared over n cubed. Make sense? Okay, so we're going to do the sigma now. And so there's 3 terms in there. And so we're going to maybe just like mentally distribute the sigma essentially. So it's going to be sigma of the first term minus sigma of the second term and minus sigma of the third term. The other thing I want you to realize is that the active element in the sigma is the I. And so as far as the sigma is concerned, the 3 and the 2 and the n squared and the n cubed are going to just function as constants. It's really only going to have an effect on the i's. Does that make sense? Okay, so I'm going to write limit as n goes to infinity. And now we're going to do the sigma. So let's just focus on the first one. So sigma from I equals 1 to n of 3 over n. So it's really, I mean, the 3 over n is just a constant, right? It's going to just view the whole 3 over n as just a constant. So the formula here, and you can see this if you look earlier, the formula for sigma of a constant is just that constant times n. So 3 over n times n will give us? 3. Yep. So, oops. 3 minus 2 over n squared. And here we're going to be sigma-ing or summing I. So if this is Gauss's little formula, or he's credited with this, summation from I equals 1 to n of just I integers is n times n plus 1 over 2. So I'm just going to write, can I distribute the n? Would that be okay? So n times n plus 1 would be n squared plus n over 2 minus, and then it's going to be 1 over n cubed, and this is where I might need your help on the formula. So sigma from I equals 1 to n of I squared, this has like a 6 in the denominator, is that right?
Yeah.
It's like n and then 2n plus? Say it again, Alyssa, sorry.
N times the quantity n plus 1 times another quantity 2n plus 1.
Okay, there we go. All over 6, right? Okay, so a little bit of simplifying here. For instance, these two 2's cancel out. So we could write, I hope, man, this is going to be hard to see. I'll try to squeeze it in down here. So limit as n goes to infinity, there we go, of, it's going to be 3 minus n squared plus n over n squared minus, the most important part of the last one is that if you multiplied everything out, and you can do this, of course, if you want, but won't the first term be 2n cubed? That's the most important part. So if you want to multiply the whole thing out, that's fine, but it's going to be 2n cubed plus ... whatever, all over 6n cubed. Why don't we care about all those other terms? Because we're about to do the limit as n goes to, oh boy, that's really hard to see. I'm sorry. I can't really move it. If I do, it erases everything. Can you see it okay? All right, I'll try to do better here. The bottom line is we just apply the limit as n goes to infinity. So the limit as n goes to infinity of 3 is just 3. What about the second term, the n squared plus n over n squared? As you apply limit as n goes to infinity, it's 1. Yeah, so it's going to be 3 minus 1 minus, and then how about the last one? 2/6 or 1/3. So it's going to be 3 minus 1 is 2. 2 minus 1/3 is 5/3. So, according to Riemann, that's the area of that. Anybody check it? You want to check it really quick? Use your calculator. Just go Math 9 and do the definite integral, and hopefully you'll come up with 1.6666666.
Yeah.
Wow.
So there you go. You can see that that's a relatively complicated process. It's far from being above you, right? You can do it. You all did it. It's just that taking the time, space, effort to do it.
First fundamental theorem.
Say again?
First fundamental theorem's faster.
Way faster. Totally agree. It's usually 2-3 steps instead of 5 or 6 steps. Okay, so that satisfies some curiosity there. I think it's fun to do that. It's fun to do a complicated process and get it right. That's always fun. Okay, well, let's take a look here at the other part of this. And of course, this is part of a video. This video wouldn't be due until like next Monday, I guess. But let's run through this. Maybe I'll save you the time with the video here. And we got about 6 minutes left. We'll see how this goes. So 4.3 continues the conversation about Riemann sums. But then we take the extra step forward to connect it with a definite integral. And that connection is quite important. I feel like you guys have already demonstrated that you get that connection, so that's great. So a Riemann sum is a collection of approximations for area under a curve. And the upper, lower, left, right, midpoint, trapezoid approximations, all of these approximations are going to be referred to as Riemann sums. So you see that on tests and quizzes, the AP test, whatever, Riemann sum. It kind of lumps all those together as just one kind of thing. So the definition of the definite integral, I want to point this out. This right here, well, it's full of scary stuff, of course, but this right here, isn't this what we've just been doing? Limit as n goes to infinity, sigma f, basically the area of a rectangle. That's what we've been working with for the last 2 examples. But then there's that thing on the left, and I want to point out a couple things about that. That funny looking delta with the double absolute value thing, that's called the norm of the interval, and it's also known as the width of the widest rectangle. The width of the widest rectangle. And of course, f of ci, that's the height of each rectangle. Delta x is the base length of each rectangle. That's the same. What I want to do is help you understand how the thing on the left and the thing in the middle are really the same thing, just looking at the coin from 2 different sides. So the one in the middle we've been working with, we've basically been saying that we want the number of rectangles to go towards infinity. Well, if the number of rectangles goes towards infinity, then the width of them would go towards 0. If you look at the expression on the left, it's saying the limit as the width of the widest rectangle goes to 0. So, okay, if the widest rectangle is approaching a width of 0, then how many rectangles would there need to be? Infinity, approaching infinity. And so you can still see that the sigma is the same, the area formula inside the sigma is the same. So it's basically looking at the coin from 2 different sides. Do we want the number of rectangles to go towards infinity, or do we want the width of the widest one to go towards 0? It's really saying the same thing, just in a different way. Both of them are equal to what we call the definite integral, which is this over here. And this is, of course, what we'll use far more often than not, way easier, right? It's the easy button for sure. So I guess we have some blanks to fill in here. So if the widest rectangle is approaching a width of 0, then each rectangle is approaching a width of 0. This means that the definite integral is an infinite summation of infinitely skinny, is the word I'd put there, rectangles. Since each rectangle is infinitely skinny, then we could informally say that we are really adding an infinite number of point width heights. Make sense? Point wide heights. So it's a rectangle with only a point of width and a certain height. That's really what we're adding up. Then an indefinite integral is a family of functions. What characterizes an indefinite integral? The plus c, right? So if you see a plus c, that's what we call either an antiderivative or an indefinite integral, and it's just a family of functions depending on what the c is. The c could be all kinds of stuff, so it's this grouping of functions. Whereas a definite integral, where you've got the limits like a and b on there, is not a family of functions. It's not really a solution because they're not solving anything necessarily. Think really, really basic.
Area?
Okay, an area is typically expressed as a number. Yeah, so a definite integral just comes out to be a number usually because it is related to area, right? It's related to area, and so hey, it's going to be a number, like 10. It's not a family of functions. It's just a number. So I think this is a perfect place to stop because when you come back to school next Monday, we got another Riemann sum we're going to try to handle. Maybe be a good time to have a little space in between, see if you can remember how to do it. But for now, the main feature would be